Full-scale structural and non-structural construction procedure of a multi-storey test building at the Engelkirk Structural Engineering Shake Centre. Module 2, Structural Foundation. A full-scale 5-storey building was built and tested at the Engelkirk Structural Engineering Centre at University of California, San Diego, and equipped with non-structural components. Specific topics that will be discussed include the construction of the rebar cages, formwork, pre-stressing, base isolation, and the pouring of the concrete. The first and primary objective of this video is to utilise the 5-storey building test at UCSD as a case study to learn the basic phases of construction of a cast-in-place foundation of a tall building. The second objective is to learn the basic concepts in preparing and installing conventional rebar and high-strength post-tensioning tendons for cast-in-place footing construction. The third objective is to learn basic requirements for falsework for cast-in-place footing construction. The final objective is to learn the basic stages of using concrete in foundation formation and the different testings that were conducted during and after the pouring of the concrete. Typical foundation structures are built below ground. Because this experiment was conducted on a shake table, the foundation was constructed above ground. Therefore, some differences from conventional foundation construction practices will be highlighted in this video. One of the most apparent differences between the 5-storey building case study and footing construction in conventional buildings is that the test building was constructed directly on a shake table, also called a steel platen, rather than on the ground. Missing in this video is the initial step of excavating the earth in order to place the foundation into the ground. When constructing a specimen on a shake table, the test structure is cast directly only to the top of the steel platen, requiring formwork to support the sidewalls of the foundation. In the field, however, shallow footings can make use of the natural sidewalls provided via the excavated earth, but formwork in the field is required if the sidewall of the foundation extends above the natural grade or ground level. Footing construction begins with the erection of formwork, which is typically a temporary stiff form that provides a mould for concrete to be poured into. After the concrete has cured sufficiently such that it is self-supporting, the formwork is removed. A number of different materials can be used to create the formwork, such as timber, metal, and plastics. In this case study, temporary formwork is constructed of timber framing and panel members. Depending on the design of the foundation, the formwork may often require both an interior and exterior segment to support the structural foundation components. In the 5-storey building test, the interior formwork is installed first. To install formwork, wood panels are cut to the appropriate dimensions and are fastened tightly with horizontal beams in order to avoid leakage or failure of the formwork. After the installation of the interior formwork panels, braces are built to resist the actual weight of concrete and the outward lateral force that develops during the curing of the concrete due to thermal expansion. After completion of the interior formwork, the exterior formwork of the foundation is constructed. Unlike traditional building construction, in the 5-storey building test box, elements were fabricated at each corner of the foundation to prevent the concrete from filling in the spaces where base isolators would eventually be installed. Base isolators are sometimes used in regions of the world where significant seismic activity can be expected, such as the west coast of the United States. When properly designed, a building supported on base isolators will observe much lower seismic forces and displacements than compared to a building fixed at its base. In this project, 4 high-damping rubber base isolators were placed under each of the 4 exterior columns of the building. These dampers were cylindrical in shape and consisted of layers of rubber sandwiched between plates of steel. Base isolators are very stiff and strong in the vertical direction, but flexible in the horizontal direction. When an earthquake occurs, the accelerations transmitted to the building is reduced and the building's natural period of vibration elongates. As a result, the isolation system can absorb more than 80–90% of the displacements imposed on the structural system, and interstory drifts, which, if large enough, can be damaging to the structure and its non-structural components, are significantly reduced. In this project, after the base isolated building was tested, the isolators were removed and the 5-storey building was fixed directly to the shake table. This was done in order to compare the seismic performance of the base isolated building in contrast to the building fixed to the foundation. Concrete cast-in-place construction requires the use of steel reinforcing bars, simply termed rebar in the field, to carry the tension forces, since the strength of concrete in tension is only 10–15% of its strength in compression. Specifications for the design, materials and placement of a reinforced concrete section are governed by guidelines developed by the American Concrete Institute. After the construction of the foundation formwork is complete, rebar cages are installed. Rebar cages can be built either on or off site and then placed inside the foundation formwork. In this project, the foundation rebars were built on site. Small diameter rebar are often bent or cut manually with a hickey, whereas larger rebar must be modified using a hydraulic machine. The rebar typically have ribs on them to facilitate a strong mechanical interlock with the concrete. Once the rebar are sized and shaped according to the specifications, they are then connected to each other, typically using steel tie wire to form a three-dimensional rebar cage. Welding of rebar cages may also be used, however it is not common, and only ASTM A706 low alloy rebar is typically ready to weld. In structural applications, pre-stressing using high-strength steel tendons are often placed in conjunction with the nominal steel rebar to improve the strength of the concrete. Two methods, pre-tensioning and post-tensioning, are often used. Pre-tensioning is the placing of concrete around reinforced tendons that have already been stressed to a desired force level. Once the concrete cures around the tendons, the pre-tension cables are cut, thereby transferring their tension forces into the concrete block and ultimately giving it additional compression strength. Post-tensioning is the placing of voids or ducts into the concrete before the concrete cures. High-strength steel tendons are inserted through the pre-made ducts and the concrete is poured around them. When the concrete hardens, the tendons are stretched or tensioned by hydraulic jacks to their desired force level. Anchors are placed on the tendons and the loading forces on the cables are released, resulting in a transfer of their tension forces into the concrete block. The benefits of pre-stressing in general are that it allows for longer spans and thinner slabs, therefore requiring less concrete. In addition, thinner slabs result in less dead load, which improves the seismic performance of the member. In this project, both unbonded and bonded post-tensioning was used. Unbonded post-tensioning allows the individual cable inside the voids to move freely relative to the concrete. This method is used less because the concrete can de-stress naturally, therefore limiting its potential to the structure. In bonded post-tensioning, grout is poured into the void after the tendon has been stressed to its desired level, creating a bond between the steel and the concrete, and allowing the reinforced concrete to reach a higher overall strength. In this particular project, high-strength rods and tendons were placed inside ducts made from PVC pipes, which were cast within the foundation. The rods were left unbonded and tensioned after placement, while the tendons are bonded with the grout. In order to ensure that the foundation and the main building structure are continuous, the reinforcing steel required for columns and walls at the lower levels of the superstructure must be built integral with the foundation. In this project, during placement of the foundation reinforcing cages, the reinforcing cages for the columns were placed and extended well into the upper levels of the building. This enables the starter rebar for the columns and walls to already be in place when the footing concrete is poured. The columns are detailed with a prefabricated welded tie tightly spaced up its height, encapsulating the vertical bars, and these are also in place when the foundation is poured to provide stability to the column reinforcing. Once the rebar cages and formwork are complete, the foundation concrete is poured. Before the concrete is poured, a slump test is conducted. This essentially consists of pouring a sample of the concrete into a small cylinder and then lifting and removing the cylinder. The amount the concrete slumps down provides an indication of the workability of the fresh concrete. Once the desired slump is attained, the concrete is ready to be poured. The concrete mix is primarily composed of cement, water, and coarse and fine aggregates. Cement is the mix binder and hardens in the presence of water. The ratio by weight of cement to water is an important indicator of the strength and workability of the mix, and typically ranges from 40 to 60%. The aggregates are small and are usually made up of materials such as sand, gravel, or crushed stone. The aggregates are used to reduce the final cost of the concrete as well as provide volume stability to the hardened concrete. In this project, the concrete was poured using a truck-mounted boom pump method. Immediately after the wet concrete mix is poured into the formwork, the concrete is vibrated to eliminate voids or air pockets. A large metal or wooden board is then used to screed the top of the concrete. This screeding process helps compact the concrete, ensuring the surface is level and smooth. It also brings near-surface water to the top of the concrete, further aiding in its finish. Finally, the concrete is thoroughly covered with a waterproof layer to control and keep the moisture content preserved during the curing process. During the pouring process, samples of the concrete are poured into small cylinders in order to test the concrete strength during various stages of the curing process. After 28 days of curing, the concrete mix typically attains its design strength, and its rate of strength gain beyond this duration is quite minimal. This video utilised a 5-storey building test at UCSD as a case study to learn the basic phases of construction for a cast-in-place foundation of a tall building. The conventional preparation and installation of rebar and high-strength post-tensioning tendons were discussed, as well as basic requirements for falsework, system formwork and safety scaffolding. Additionally, standard methods to pour concrete into the foundation were highlighted, including the different tests that are conducted during and after the pouring of the concrete. Because this experiment was conducted on a shake table, some differences from the conventional foundation construction practices, such as the use of base isolators and the need for formwork, were demonstrated in the video.